Our next chapter, chapter 10, is simple harmonic motion and elasticity. What is simple harmonic motion means? Simple harmonic motion is a type of periodic motion. It's a simple harmonic motion is a type of it's a periodic motion. In addition, it has other features. So if you apply a force to an object, the displacement of that object directly proportional to the displacement. So therefore, this periodic motion, I will give you some examples in next few slides. So it's a periodic motion. In addition, uh, a motion acceleration or force directly proportional to displacement. If I apply a force to an object, the displacement of that object is proportional to the applied force. Directly proportional to the force, or force is proportional to displacement. And the other part of this topic is elasticity. So what is elasticity? So elasticity, let me give you an example. Let's say we have like a small piece of sponge, and when you apply a force to this sponge, you make some sort of a deformation. This nice square shape. When you apply a force, you can bend this, and when you remove this force, it will go back. So elasticity is a feature of an object. When you apply, it will deform, but when you remove that force, it will go back to its initial shape. So relationship between solid body deformation and the force that cause the so it's a relationship between solid body deformation and the force. So the force and the deformation, the relationship, we call it elasticity. It's a simple harmonic motion and elasticity. Simple harmonic motion is a periodic motion which has a force which is proportional to the displacement. In this example, this figure in the middle, let's say A, we have a string. One end of that string is attached to a wall or a vertical surface, and other end it just stays, nothing attached to the other end. So this is sort of the unstrained length. When it is relaxed, it has a particular length. So we can hold from this end, or we can stretch, or we can suppress. So in order to do that, to move this unstrained spring from its unstrained location, we have to apply a force to make it stretch, or we have to apply a force in this direction to make it strain. So every time, whether we going to stretch or strain, we have to apply a force direction of you want to apply. So every time, in this case, let's say B. So if you apply a force, you see it expand length x, and when you apply a force in negative x direction, you contract again about the same amount. So the applied force along x direction, which is sort of proportional to the length stretch. It can be stretch or strain. So we can write an equation. So applied force always proportional to the length, strain or stretch. So if you write an equation, so applied force is equal to a constant times relax or strain length. So this constant, we call it spring constant, which is a constant for a given elastic material. So like a spring has a spring constant. If you take a sponge, it has a constant. So K is applied force divided by the length. So applied force, unit is Newton, and length, units is meters. So newtons per meter is the units of spring constant. So this is the first equation we learned. Applied force along a particular direction is equal to the spring constant times the length. It expand or stretch. So if you know the spring constant of this given spring, we can apply a force, and then we can check the relaxed length or strained length. So using this equation, if applied Kx, we can calculate the tire pressure, which is proportional to the force. So if you know the spring constant, which is given 320 newtons per meter, and if you know the length, it expands, so 2 centimeters. If you make it divide by 100, we get meters. So 0.6 Newton. Yeah, actually 320 times 0.02 is not 0.6 in so the right answer is 6.4 newtons. That's the applied force by the air in the tire. Next topic is Hooke's law. Today's lab is based on this law, Hooke's law, and we're going to use this equation. This equation is very, very similar to the equation we learned in the previous slide. So applied force along x direction is equal to spring constant times x. So in the same example, let's say this is in this spring is at unstrained. This is the unstrained length. You apply a force to make it stretch. So you apply a force along to make it stretch by distance x. So if you let this spring go, it go back to its initial position. So if you pull this spring and let it go back to its initial position. So what is the reason why it going back? Because inside the spring can cause a opposite force. We call it restoring force. This restoring force cause this spring to go back to its initial position. Same thing, if you apply a force to stretch this spring by X, if you apply a force, to along negative X direction, you can compress this spring by distance X. But if you let this spring go, it will go back to its unstretched position. So that force, we call it restoring force. So this restoring force is same as the applied force but opposite direction. So therefore Fx is the restoring force is again equal to the displacement times K. You apply a negative value number, negative sign, because applied force and the displacement, restoring force and the displacement are two different directions. Restoring force in one direction, X is in opposite direction. It's basically the opposite equation we learned in the previous section. So this equation, we call it Hooke's law. So restoring force is equal to spring constant times displacement. So you can write similar equations for y direction, ky. So the displacement along y, force along y. So it's basically the same equation, displacement along x, spring constant times the displacement. This is a experimental setup we use to study simple harmonic motion. In this setup, we have a rotating circular table, and it has a small sphere attached to that spinning circle, and it spins along counterclockwise direction. And over here you have light bulbs, and it falls because of the light. You will see a shadow on this film. So if this ball starts rotating, you see this shadow also moving because this film also moving in this direction. So let me use a different color. Depending on the location of this sphere, you see a corresponding place on the film. So if the film ball is here, you see a spot here. So if it is here, you see a spot here. So if you plot, or if you track the position of the ball on the screen or the film, you see it's like a wave-like shape, like this. So if you match with the position of the ball, so ball is going around a horizontal circular orbit, and when you track the position, it will gives you a wave-like motion. Here you see the top view of this circle, and you see a arbitrary position of the ball. And if this is the radius, or A, and this length, which is the length or width of the wave, because we see a wave like this, and depending on the location, we can measure this length. So which is, if you know the angle and if you know this radius, which is A cosine theta. So this position, which is equal to x, is A cosine theta. A is the displacement. So for a wave, the maximum height or maximum displacement, we call it amplitude. And the period, time required for one cycle from here to here, we consider as a one cycle. We call it time required for one cycle period. It depends on where you start measuring. So if you start measuring from bottom to the next bottom is one period. Time required for one cycle is period. You use uppercase T for period. And frequency, number of cycles per second. We call it frequency. So there's a relationship between period and frequency, which is 1 over T is frequency, or T is 1 over frequency. So these are identical. So we need these three: amplitude, T and F, because the equation we derive is displacement equals amplitude cosine theta. Theta is the angular displacement. This is the linear displacement. So in next slide I'm going to replace this theta angular displacement with another variable we learned in the previous chapter. Okay, we derive an equation for the displacement of an object in a simple harmonic motion. The displacement we can write in terms of x. X is A is the amplitude of the wave, cos theta. So angular velocity is theta, which is equal to omega times t. Angular velocity is equal to omega times t. And similarly, we can write velocity of this ball rotating around this circle, and if you get the Vx component in terms of the tangential component, we already know the Vt tangential component. The tangential component of an object is radius times omega. So in this case, radius is r, a amplitude, a omega. So Vx is Vt tangential component of the velocity or speed times sine theta. So you get a negative because Vx is on the negative x direction. This is your positive x direction. So if you substitute r omega or a omega, so you get negative a omega, which is, and sine theta is omega t. So basically speed along x direction is negative a omega sine omega t. Similarly, we can write a equation for the acceleration for an object on a simple harmonic motion, and I will show you how to write the acceleration along x direction in the next slide. Okay, so we know if an object in a circular motion, we have a centripetal acceleration. We learned that, which is v square over r. Okay. So v is the linear velocity speed, which is equal to r omega. Therefore, acceleration is r square omega square, because I'm going to replace v with in terms of r omega divided by r. So r cancel, we have r omega square. So here r equals a amplitude, a omega square. So ax, acceleration along x direction. This is your AC, centripetal acceleration, cosine theta, and we get a negative sign because of the negative direction. So AC centripetal acceleration is a omega square, we just derive. Theta is omega t. So therefore ax equals negative A omega square cosine omega t. Okay, so frequency of vibration, how many oscillations or how many waves occurred in 1 second, so which is W. So we can derive this using a combination of Newton's law and Hooke's law. So Hooke's law is force is equal to K, the spring constant, times displacement, which is equal to, according to Newton's law, force is mass times acceleration. So if you substitute K, x, which is A cosine omega t, which is equal to, so if you substitute, you can get kx equals A cosine omega t, which is equal to m times ax is negative A omega square cosine omega t. So there are several things you can cancel on this equation. Omega t cancel, negative cancel. So you have Ka, which is equal to ma omega square. So a also cancel because it's common to both sides. So omega square. So k over m square root is omega. So this is the frequency of vibration. In previous chapters, we talk about moving objects. If an object has a speed, we can talk about kinetic energy, and also if it is moving from one location to another location, we can talk about the potential energy, and then we derive a conservation of energy. Final energy of the system is equal to initial energy. So any object, we can use the conservation of energy for simple harmonic motion objects on periodic motion, and we can write the final energy and initial energy in terms of spring constant and also the displacement and the frequency. So I'm going to show you the final result, how you use the total energy of an object in simple harmonic motion. Okay, this equation shows the final energy and initial energy of an object in simple harmonic motion. So you have so many terms, potential kinetic energy for before and after, and this equation is very much similar to the equations we derived before for conservation of energy, except this term. So 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 I'm not going to ask any questions from this equation in your test, or probably I will give you a homework question, but I don't plan on adding any questions from this section for your test. Okay, so this is like a molecule. You see there are atoms. There are several atoms, like 8 atoms connected with springs to each other. In reality, there are no springs attached to atoms, but we can assume this model, they are we know these atoms constantly vibrating, they are in motion. So, and also in a molecule, those atoms bound together. So we can assume, or we can come up with a model like a spring model. Each of these atoms connected to another atom using from a spring, and since we already know the velocity, acceleration, and position, we can calculate the position of atom using those equations. So this table shows the Young's modulus, the stress over strain for different materials. For aluminum, the Young's modulus is 6.9 times 10 to the power 10. So Pyrex glass, the modulus is large, 6.2 times 10 to 10. So titanium, tungsten, these values, Young's modulus is large value. And some materials like a bone, is a small value compared to titanium or tungsten. So when you change the volume deformation, change of volume, initial volume to the volume change, the ratio, the strain, we call it bulk bulk modulus, and we use beta for bulk modulus. So this table shows the values for bulk modulus for aluminum, volume change, and liquids, and a couple of other like nickel, nylon. So it's a small value. It's easy to change the volume with a smaller force compared to like copper or diamond. Diamond is even harder. So in this table shows stress over strain. Stress is force applied on area or volume or length, and strain is the ratio of length to initial length change to or area change, initial area, or volume change, delta V to initial volume V naught. So this ratio, stress to strain, is proportional to a certain period. During this, from up to this point, when you really remove that force, any object can go back to its initial shape position. But after this elastic limit, we start deform the object, and after one point it will break. So after that point, that object can, if you have like a wire, you can apply a force and you can stretch. But if you, after this elastic limit, if you apply further force, at least it will break.